Chapter 2, Exercise 29. Hence, let G be an open subset of R. Consider maximal open intervals contained in G. Show that distinct maximal open intervals within G are disjoint. Note that what is referred to as a segment in the book is more commonly called an open interval today. Solution. We first prove an auxiliary statement. Let G be a non-empty open subset of R such that for any u, w in G, with u less than v less than w, it follows that v in G. Then G is an open interval, possibly unbounded. In other words, G must be one of the following: I, R, II, negative infinity to b, exclusive, for some b element of R, III, exclusive a to infinity, for some a element of R, IV, non-inclusive a to b non-inclusive, for some a, b in R with a less than b. To prove this statement, we consider several cases. I. If G is unbounded both above and below, then for any x in R, there exist points u, w in G such that u less than x less than w. By assumption, x in G, so in this case, G equals R. II. If G is bounded above and unbounded below, let B equal supremum G. Since G is open, we have G subset of this. Indeed, if it were B element of G, then, since G is open, there would exist epsilon greater than 0 such that this, contradicting the choice of B. Conversely, if x element of this, then x is neither an upper nor a lower bound of G. Thus there exists points u, w in G such that u less than x less than w. By assumption, x element of G, so G equals this. III. Similarly, if G is bounded below and unbounded above, then G equals this for A equals infimum G. IV. If G is bounded both above and below, using the same technique as before, we can show that G equals this, with A equals infimum G and B equals supremum G. Now, let G be an open subset of R. If G is empty, then the result trivially holds. We take an empty union, which is by definition empty set. Hence, assume that G is non-empty. For each x in G, define I of x as the union of open intervals J such that x element of J subset G. Such intervals exist since G is open. We will prove that I of x is an open interval. Since I of x is a union of open intervals, it is itself open, Theorem 224a. Consider points u, v, w such that uw element of Ix and u less than v less than w. There exists open intervals j1, j2 such that this. Since this, the set j equals this is an open interval, then uw element of j and u less than v less than w imply this. By the auxiliary statement, I of x is an open interval. By construction, I of x is the maximal open interval containing x that is contained in G. Now consider the collection set J alpha of all distinct open intervals among the Ix's. Note that for different points x, y, and G, the intervals I of x and I of y may coincide. We will prove that distinct open intervals, here and here, are disjoint. Suppose, for contradiction, that this and that are distinct, and that this. Then this is an open interval and satisfies this. Since I of x is the maximal open interval containing x and contained in G, it follows that this, and thus this. Similarly, this implies that, and hence this. Therefore, I of x equals I of y, which contradicts the assumption that these intervals are distinct. Thus, the collection set J alpha consists of disjoint intervals. Since every point x in G belongs to some I of x and each I of x equals some J alpha, it follows that G equals this. It remains to show that the collection set J alpha is at most countable. For each alpha, there exists a rational point J of alpha, element of J alpha, by theorem 120b. If alpha 1 does not equal alpha 2, then this, implying Q of alpha 1 does not equal Q of alpha 2. Thus, the index set alpha is in one-to-one correspondence with the subset of Q. Since Q is countable, corollary to theorem 213, the collection set J alpha is at most countable by theorem 2.8. Comments. There's another approach to this exercise. Every metric space can be written as a disjoint union of its connected components. See the comment to example 20. Since neighborhoods in Rk are connected, a connected component of an open set G subset Rk is open. So every open set G subset Rk can be written as an at most countable disjoint union of connected open sets. On R, the only open connected sets are open intervals, which proves the needed result. The previous comment gives a generalization of the result of this exercise to Rk. Every open set G subset Rk can be written as an at most countable disjoint union of connected open sets. This result is less informative, as in Euclidean spaces of dimensions greater than 1, there are much more different types of connected sets comparing to the real line R. See comment to example 20. For example, an open set G subset R2 may not have a representation as a disjoint union of open two cells. Here is a picture. Two distinct largest open two cells containing X. Thanks for watching.